Hello everyone. In the last lecture, we discussed about the quantum theory of Raman effect, and we saw that the Raman transitions take place through a virtual state. Thus, the mechanism of Raman transition is different from that of a spectroscopic transition. For a rotational transition, we have an initial state and a final state, and there will be transition from initial to the final state. The probability of this transition is proportional to the absorption process. For a Raman transition, as we saw in the last lecture, there is a virtual state in addition to the initial and final state. At first, the molecule goes from the initial state to the virtual state, then it comes back to the final state. So in this case, the probability is proportional to the product of these two transitions. That is, the transition probability of a Raman transition is different from a normal spectroscopic process. As this probability determines the selection rule for Raman transition will be different from the corresponding absorption transition. So, thus, when the initial and the final states are rotational levels, we know the selection rule for rotational spectroscopy, that is delta J equal to plus or minus 1. But in the case of rotational Raman spectroscopy, the selection rule will be delta J equal to plus or minus 2. In rotational Raman spectroscopy, we will focus on linear diatomic molecules. As we know, for the rigid rotor model, the energy of rotational levels of molecules is given by Ej equal to Bj into J plus 1 centimeter inverse, where J is the rotational quantum number. Following the selection rule, delta J equal to plus or minus 2 for Raman transition, we have delta Ej equal to Ej plus 2 minus Ej, or B into Ej plus 2 means we are giving Ej plus 2. In case of J, we are placing J plus 2, and J plus 2 plus 1 is J plus 3 minus Bj into J plus 1 for the Ej. For Ej plus 2, we are giving this, and for Ej, this. The difference will give B into 4J plus 6 centimeter inverse, which is known as Raman shift mu bar. That is the shift from the excitation wavelength or wave number. So, Raman shift mu bar is equal to B into 4J plus 6 centimeter inverse. Here, J can take values from 0, 1, 2, etc. Now, let us find the allowed Raman transitions in the rotational levels. Here you can see the rotational levels 0, J equal to 0, 1, 2, 3, etc. up to 8, etc. And the transition according to the selection rule for delta J plus 2, it is first transition from J equal to 0 to J equal to 2, next 1 to 3, next 2 to 4, and for delta J equal to minus 2, from 2 to 0, 3 to 1, 4 to 2, etc. Thus, with respect to an incident Sorry. Then we are dealing what is Raman shift. We know Raman shift is, we have calculated what is the Raman shift, which is B into 4j plus 6 centimeter inverse. And for the transition from j equal to 0 to j equal to 2, what will be the Raman shift? We have calculated in rotational spectra that the frequency of transition there is 2b into j plus 1, and we put the j value as the initial state. Here also for b into 4j plus 6, we are taking the initial value 0, and the first shift line will be 6b centimeter inverse. This is the first transition, j equal to 0 to j equal to 2. What will be the next transition? J equal to 1 to j equal to 3. What will be new? New will be b into 4 into 1 plus 6, that is 10b. For a transition from j equal to 2 to j equal to 4, nu bar equal to 14b centimeter inverse, etc. Thus, with respect to an incident frequency or wave number, nu bar excitation, where nu bar excitation means this excitation radiation, that is the radiation used for the excitation process. With respect to this radiation, there will be a Raman shift in two directions for the different cases of scattering. That is, if the molecule gain rotation energy from the photon during collision, the scattered light loses energy and the Raman shift is towards the lower wave number of the excitation frequency or wave number, that is nu bar excitation minus b into 4j plus 6. While if the molecule loses rotational energy to the photon during collision, we will have a series of lines to the higher wave number, that is the Raman shift is towards the higher wave number, which is mu excitation plus b into 4j plus 6 centimeter inverse. Hence, the wave numbers of the corresponding spectral lines that we can observe in a rotational Raman spectrum are given by nu bar equal to nu bar excitation plus or minus b into 4j plus 6 centimeter inverse, where the nu bar excitation is the wave number of the exciting radiation. The plus sign refers to the anti-Stokes line. The plus sign means it goes to the higher wave number side of the excitation radiation, and the minus sign, which means it goes to the lower wave number, it is known as the Stokes line. Now, let us see how the rotational Raman spectrum look like. There is nu excitation, nu bar excitation in the middle, and the Stokes and anti-Stokes lines distributed in two sides like 6b, 10b, 14b, etc. in both sides. And now, if we look into the spectrum, we can see that the first line is shifted by 6b centimeter inverse from the excitation wave number, both on left and right. And all the other lines are shifted by 4b centimeter inverse. This figure shows the typical rotation Raman spectra where The difference of the first line on either side from the excitation line is 6b centimeter inverse, while the separation between successive lines are 4b centimeter inverse. The relative intensities of the lines are indicated. As you can see, there is a difference in the height of the peaks or lines. That is, the relative intensities are indicated assuming the population of various rotational levels. Thus, the rotational Raman spectrum of a linear diatomic molecule consists of a series of lines with constant gap 4b centimeter inverse on either side of the excitation wavelength of the radiation. It may be mentioned that homonuclear diatomic molecules are microwave inactive as they have no permanent dipole moment, and as such the determination of the rotational constant or the bond length of these homonuclear diatomics cannot be determined using rotational spectroscopy. But rotational Raman spectra can be obtained for these molecules as there involves polarization due to incident light, and this Raman activity depends on that polarizability only. So it provides a method for the determination of bond length of all diatomic molecules which are not microwave active. By this, we are concluding the rotational Raman spectroscopy. Thank you, my dear students.